Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at a Maths Olympiad question. We've been asked to do more of these and they're great fun, so let's do this. So here's a problem. A plus B plus C are rational numbers and A plus B cube root of 2 plus C cube root of 4 is 0. We're required to prove that A equals B equals C equals 0. So the only way this can happen is if A, B and C are 0. Okay, first we're going to write the cube root of 2 as alpha. Notation always helps. Creating good notation always helps. This means the cube root of 4 is the cube root of 2 squared is alpha squared. So our equation becomes A plus B alpha plus C alpha squared is 0. So if we can show that 1 alpha and alpha squared are linearly independent over the rationals, then we'll have our result. Because A equals B equals C equals 0 is clearly a solution, but if these three are linearly independent, it will be the unique solution. Okay, so how are we going to do this? So Q of alpha is a field, and it's an extension of Q. The field of rational numbers is actually a proper extension because alpha is not a rational number. Do you know the proof? It's elementary. It's a bit like the proof that the square root of 2 is not a rational number. X cubed minus 2 is the minimal polynomial of alpha. X cubed minus 2 is irreducible over the rational field by Eisenstein's criteria, with 2 playing the role of the prime. So we need a prime that divides all the coefficients except the leading one, and the square of the prime does not divide the constant term, and 2 plays that role. So this polynomial has degree 3, and so the extension has degree 3. Alpha, alpha squared are roots of the minimal polynomial, so 1 alpha, alpha squared constitute a basis of the extension field when considered as a vector space over Q. That means these three are linearly independent, and that means we've got it. A equals B equals C equals 0. We're also going to give an elementary proof because the people sitting in the Olympiad are pre-university. So to obtain a contradiction, let's assume that in this expression C is not 0. So in this case, we take A and B alpha from both sides, and we get A squared equals minus A minus B alpha, and then we divide by C over C. And we're going to write that as P plus Q alpha. So here we can rearrange this as a quadratic. Alpha squared minus Q alpha minus P equals 0. Now this should ring alarm bells because we know that the minimal polynomial of alpha is a cubic. So it should not be able to satisfy a quadratic. And that was the argument I did use in a previous version of the video, although one viewer rightly pointed out that that wasn't really an easy step because we're still using the concepts of minimal polynomial, which is not really an elementary concept. So instead, we're going to use the Euclidean algorithm for polynomials over a field. So we're going to divide x cubed minus 2 by x squared minus qx minus p. And we're going to get a non-zero remainder here, fx plus g. This cannot be 0 because we know x cubed minus 2 is not reducible in the rational field. We've shown it by Eisenstein's criterion, but we can also show it directly, and we will do on the last page. Okay, so we got this expression, and then we're going to substitute alpha in for x. And what that means is on the left, we've got alpha cubed minus 2, which goes to 0. The quadratic goes to 0, so we're left with f alpha plus g is 0, or alpha is minus g over f, because both f and g must be non-zero. Because they can't both be 0, and then if one of them's 0, the other one's going to be, so they've both got to be non-zero. So alpha equals minus g over f. This cannot be the case because alpha is not rational. So that means c was 0 all along, because if c is non-zero, we get a contradiction. So now we've got a plus b alpha is 0. If b were not 0, alpha would be minus a over b, again as a rational. So b must be 0, hence a is 0, and we're there. Okay, and then how does x cubed minus 2 actually factor? So Eisenstein's criterion has shown us that x cubed minus 2 is not reducible in the rationals. But let's just look at how it actually factorizes in the real number field and the complex number field. So Again, with alpha as the cube root of 2, we know x minus alpha is a factor of x cubed minus 2. And then we can do a polynomial division in our heads because this is the Olympiad. And we get x cubed minus 2 is x minus alpha times x squared plus alpha x plus alpha squared. Let's just multiply that out to satisfy ourselves it works. So x times x squared is x cubed. And then let's look at the x squared terms. You got minus alpha x squared here plus alpha x squared there. They cancel. Let's look at the x terms. You've got alpha squared x here minus alpha squared x there, they cancel, and then you've got minus alpha times alpha squared minus alpha cubed minus 2. So it works. X cubed minus 2 is this times this. So this is how it factorizes in the real field. The discriminant of the second expression is alpha squared minus 4 alpha squared, which is negative. So we've got two complex roots, which are written here just by the quadratic formula, minus b plus or minus square root b squared minus 4ac over 2a. And so we actually got three roots, these two roots and alpha, and as we can see, these are the cube roots of unity multiplied by alpha, because if this was x cubed minus 1, we'd have the cube roots of unity. So what this shows us is, it shows us that x cubed minus 2 really is irreducible in the rationals, but it also shows us how it factorizes, which is kind of nice. I hope you like this video. I really like making it. Please subscribe and hit the notification bell if you want to see more. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.